Professor Bialis here. In this video we're going to be talking about section 2.1, which starts the main equation solving chapter in this text. In this section though, we're just going to be talking about algebraic expressions and how to manipulate them on a very basic level. Okay, before we get into manipulating expressions though, let's talk about what an expression is made up of. And that is a bunch of terms. So let's look at that. Okay, now a term in a mathematical sense is a number, a variable, a product, or a quotient. Any of those things would denote just a single term. So a number could be a 5. That's a term. A variable could be an x. A product could be, like, let's say, a negative 3x. A quotient could be x over 5. Those are all examples of terms. Okay. Now, first thing I'm going to ask you, because this is going to be something we need to be able to identify in later sections, is how many terms are there? Okay, and let me give you an expression. Let's say we have 3x squared plus 5x minus 2. Okay, in this case there are 3 terms. How I like to divvy these up and identify them is like so. 2 and 3. Notice I included that sign right in front of it with that number or expression right after it. Okay, so I have a positive 3x squared, a positive 5x, and then a negative 2. Pull it together, I have a 3x squared plus 5x minus 2. Think of when you have a sentence in the English language. A sentence is made up of a bunch of words. Each word has its own definition, but if you pull it together, it has a complete thought. Same idea here. Positive 3x squared, positive 5x, negative 2. Together, 3x squared plus 5x minus 2. Okay, so you can kind of go back and forth between, a minus and a negative. How about this one? How about that? As written, 1 term, because we've got this product as a single term. Now, if we were to distribute that, which we'll talk about a little bit later in the section, then we would have multiple terms. But as it's written, we have a single term here. Okay, when we get into clearing fractions and equations, that's going to be very, very important distinction with how many terms are in that expression at that moment. Okay? Now, after how many terms, let's talk about like terms. Okay, now like terms are terms that have the same variables with the same exponents attached to those variables. Okay? So the question I'm going to ask you here are these like terms? Okay, I'll give you something like this. How about 3x and 7x squared? Okay, in this case, the answer is no. The reason being, they both have an x, they both have the same variable, but this is an x to the first, this is an x squared. They don't have the same exponent. So those are not like terms. How about this? In this case, again, the answer is no. They both have x and y. They both have a square, but the square is in a different position. X squared y, x, y squared. Those are different terms. So we wouldn't be able to do anything with those. One last one. How about those? In this case, yes, those would be like terms. The order that you write that does not matter because you have that commutative property, okay? Remember, these are understood to be multiplied together. A 12x cubed y squared is a 12 times x cubed times y squared, okay? So order does not matter. The contents match. You've got an x cubed, y squared, they're like terms, okay? One other thing before we move on, I want to make sure that we're okay with the terminology here. These are all terms, but a term has what we call a coefficient, okay? So this term 3x has a coefficient of 3. That's that numerical value that's in front of the variables, okay? When we have a term like this -2, you could say that -2 is the coefficient, or you could say that this -2 is what's called a constant. Okay, when there's no variable attached to it, we would call that the constant term. Okay? Now, we know what terms are. We know what like terms are. Now, let's move on to simplifying expressions. And this is really the meat and potatoes of this section. So I'm just going to say simplify. Now that instruction simplify is very broad. That can mean a lot of different things depending on what you're doing. In this case, what that means is combine like terms. Okay? So let's say we have an expression like this. Let's say we have 3x squared minus 7 plus 2x minus 4x plus 5. Okay, right now we have 1, 2, 3, 4, 5 terms all laid out. All we want to do is consolidate these like terms, pull them together. Okay, really all we're doing is organizing. Okay, if you have that junk drawer that you have in your house, I think we all have a junk drawer in our house. If you ever want to clean that out, what do? You dump it all out, right? And then you just pull things together. That's all we're doing here. This is dumped out. Now what we're going to do is start to the left, work our way to the right. I have an x squared term. There is no other x squared term. So I just bring it down. Okay. Next, I have a constant term. I have another constant term here. So what I have is a -7 plus 5, which is -2. And then I have an x term and another x term. -2 minus 4 is -2x. Notice how I marked this up. This helps you pull things together, and also I can step away now and say everything is marked, I didn't miss anything. Now, at this point in the game, if they don't tell you otherwise, this is perfectly fine writing it this way. However, try to get in the habit of writing it in what's called descending order. What that means is I start with the highest exponent term, that's a 2, then I descend down to a 1, and then I descend down to nothing, okay? So it descends down in the order of exponent. Again, in this section right now, either of these would be fine. This is a little bit better though, so try and get in the habit of writing it in that order. Okay? How about this? Now think back to that junk drawer example where I said you dump it out and then you pull it all together. Okay, this was dumped out for us. This isn't. Okay, what we have to do is first distribute anything that we can. That right now, this is all held together as a product right here. We can't really do anything with it as it stands. So the first thing I'm going to do is distribute, and look at what happens. Now I have just a line of terms that I can pull together whatever I need along the way. So I start over here. I have an x term. I have another x term. 2 plus 12 is a 14x. Now negative 15 plus 15 is what? It's a 0. What I see some people do is they put that plus 0 there. There's nothing wrong with that. However, if it's not going to help you, and we'll see, situations, a little later where we're going to want that 0, just so we have something tangible to work with. But in this case, honestly, all I would do is just leave it off. And as a matter of fact, I would just cross those off, and your answer is simply 14x. That's why we call it simplify. We take an expression that looks like this, and we make it simpler into something like that. Okay? Let's do one more like that. Let's say that. Okay, first thing we do is again distribute to lay out all those quantities. So I bring down the 4, then I distribute the 5. And now here, what am I distributing? Technically what we're distributing when there's nothing in front of this, there's a 1 there. So this is a negative 1 that we're distributing. If you don't really need that or want that 1 there, you could just think of as putting a negative sign on each of those terms. Either way though, we get negative 3x minus 8. I laid it all out. Now, keeping in mind that I want descending order, I'm going to jump to this. I'm going to take this x and this x. 5 minus 3 is 2x. And then I'm going to take all these constants and pull them together. 4 plus 10 is 14. 14 minus 8 is 6. And then there is your answer. And guys, when we combine like terms, notice like these two, I didn't mess with that x. I treat the x almost like a label. I've got 5 apples minus 3 apples is 2 apples. Okay, same thing with the x's and all these variables that we go along with. Okay, how about something a little different? How about that? Now this is a little different because they're giving you those words in between that we have to first translate into a purely algebraic expression before we can work with. Now, subtract this from that. Remember when you use that phrasing, subtract from, that from portion starts the problem. And then we take from it after the fact. So what we have is 2x plus 3 to start, and then we're subtracting the 5x minus 1. Now, here's a little bit of an issue. As it was written up here, notice how these expressions were naturally separated by these words that were in between. Now, it looks like this just is one big mixture of a bunch of terms. When you translate, we need to first visually separate those quantities that we originally had separated given to us. So what I mean by that is, what I would do here is I would say this minus that. That changes the problem quite a bit. So we need to first hold these together because you are taking the 5x minus 1, this whole thing, from this whole thing. Now is when we would lay it all out. So I would just drop this out because 2x plus 3 is just 2x plus 3. But then I'm subtracting each of these. So I've got minus 5x and then a plus 1. That's a different problem than I originally had before I put those parentheses in, because now I have that plus 1 at the end. That's very important. So when you start with these words here, throw the parentheses around it, just so you don't forget. Okay? Now, combine like terms. 2 minus 5 is negative 3x. 3 plus 1 is 4. And there's your expression. Okay? The last thing that they throw at you in this section is some more translating. And we've talked about that in the past. You've practiced that in the past. But there's just one example that I want to be clear on. And that is going to be this. The difference of a number and 4 divided by 7. The difference of a number and 4 divided by 7. Now again, this is just an expression. There's no is something. That is would mean equals, so you would have an equation. So this is just translate through. Okay? Now when we translate through this, I want you to pay very close attention to not only this word difference, but also this comma right here. The punctuation with that comma always tells us to pause. Okay? Mathematically, it's telling us the same thing. It's telling us to stop, do what we've said already, then carry on from there. Okay? So, I have a difference. Difference means to subtract. So I'm going to subtract a number and 4. Okay? So I'm taking a number and 4 and I'm subtracting. But that needs to happen first. Then I divide by 7. Okay? So that's why it's important you pull this together. Now, to make that writing a little bit easier, what we typically do is we don't show those parentheses. This is how we do it. Remember, division can be shown as a fraction. So I could write it like this instead. I'm going to take the difference of a number and 4, and I'm going to take that whole thing divided by 7. This is not wrong as long as you have those parentheses. This is more of the typical way that it's written algebraically, though. Okay? So again, perfectly fine. This is a little bit better. Okay? Now, I want you to see a little change here. What if I did this and I took away that comma? Now read it. The difference of a number and 4 divided by 7. That's the same wording, different flow. Without that comma, the difference of a number and 4 divided by 7. Do you see that? Do you see how that changed? And all I did was take away a comma. So please pay attention to the punctuation. Those commas really tell you a lot while you're going through these problems. Okay? It's all about the detail. Other than that, there's not much that I really need you to take out of this section other than being able to identify separate terms and then practice that combining of like terms. It's a very simple thing to do, but if you make silly calculation mistakes or you distribute incorrectly, that's really going to wreak havoc on your understanding of later sections. Okay? So, as always, work hard. Let me know if you have any questions, and I'll see you next time.